Yeah, let's start with today's presentation, and uh, we'll just recap a bit what we have been discussing over the past two lectures. So yeah, we first saw the concept of IVC, where we have some computation which is getting repeated, and at each step we input some new parameters into the function. Then we wanted to snark this IVC. So to do that, we have kind of a modded f. We modify our function where one part of the function is doing regular computation, another part of the function is doing this recursive proof, and we could also put some part of the verifier circuit inside this snark, and that reduces some computational overload, and this is done in Halo 2 and subsequent works. And in Nova, you just fully embed this verifier circuit into the function f dash or into the modded f dash. So the function f dash here, which you see in Nova, is actually doing the incremental computation, which is taking this some input, giving some output for the next iteration, and it is also doing the verifier work. So it also has this verifier circuit, and we'll see later exactly how this is embedded. So in Nova, we have this concept of a running instance. So we have some relaxed R1CS, and at each step, so this horizontal line is this relaxed R1CS, which is running instance. And at each step, we inject our function f, which computes this yi for each iteration, and then we fold this function along the running instance. So we fold this R1CS, which comes from the function, into this running instance. And at each folding, we also have to make sure that this folding is done correctly, and this is verified. This folding is verified by the function at the next step. And once we have folded all the instances, we produce a snark proof, which convinces the verifier that this computation was done correctly. But the folding verification happens at each step itself. So at each step, the future f or the current f is verifying the folding of the previous step, and at the end we just prove by a snark proof that the final folding was done correctly, and that the functions were calculated correctly. So let's also recap the relaxed R1CS protocol, where we wanted to have where there is a prover and verifier, and the prover is trying to prove that he has folded to relaxed R1CS instance correctly. So he does that by first sending or committing to these cross terms, which is denoted by this T, and then the verifier sends a random challenge, and then they both compute the witness, the slack term, and then the prover convinces the verifier that the folding was done correctly, because he knows some secret witnesses. And it is very important that the random number is generated after the prover has committed to these cross terms. Otherwise, the prover can always cheat. So first, the prover commits to these cross terms, which is T, and then the verifier sends this random number. So now let's go ahead and see what the verifier keeps track of at each step. So at each step, the verifier keeps track of the number of rounds, or the ith round, which is happening at the current step. And it also tracks the output of the previous round. So this yi minus 1 is the output of the function when we output of the function from the last step. And the verifier also tracks the current function or the current output. So this is yi, which the f is evaluating at the current step. And then the verifier keeps track of the statement, the committed witness, and the slack terms, and this U, which is the scalar in the committed relaxed R1CS. And the prover claims that the folding was done correctly. So the prover has this running instance, which is capital U, and it is a relaxed R1CS instance. So we have this E, which is the slack error term, and this scalar. And then the prover also has this UI, which is the current R1CS, where the slack error is 0 and the scalar is just 1, because this is the simple R1CS relation. And the prover claims that he is able to fold the running instance into this current R1CS instance. And one thing to note is that the current R1CS instance is generated by when we run this function over the previous output to get some current input. So when we run this function f over the previous input yi minus 1, it gives us some current input. And this is converted into this R1CS relation, which is u small ui. And then the prover just claims that he can fold the current R1CS with the relaxed R1CS. So now let's see how the protocol works for this running instance and R1CS version. So at each step I, we have that the prover sends to the verifier the current output, which is yi, and the committed witness I. So the prover gives commits to the witness and also sends the current output, and the verifier just now updates the his x, or the statement variable, as the previous output with and the current output. And the verifier now has this R1CS relation, which is the same as the prover, which is A Z1 times B Z1 equals to C Z1. And this is over the committed witness terms. So the verifier has the commitment to a witness, and the prover actually has the full witness. So once the verifier knows the commitment to the witness and the current output of the function, then the prover also commits to the cross terms, which will so that the folding can happen. So the prover sends this commitment to the cross term, and now the verifier can verify the folding of the small ui with this capital UI. Also, one thing to note here is that when we are starting, when I equals to 1, or when the process starts, the R1CS instance is the running instance. So we just update the R1CS with the relaxed R1CS. So at I equals to 1, this capital UI is just the R1CS. But once each iteration happens, the running instance gets updated, and it gets folded into the current R1CS instance. So are there any questions up until now? So now what happens is that now the verifier and the prover, because we want to make it a non-interactive protocol. So now the prover and the verifier both choose a random R, and this random R is just calculated using the public inputs, which public values, which both the prover and verifier knows. So R is just hash of these U1 and U2 and the cross term. So the cross terms, the commitment to the cross term is known to both prover and verifier, and U2 is just 1, because the R1CS because U2 is the scalar term for the R1CS and U2 is just 1 for R1CS, and U1 is the scalar term for the running instance. So now after the verifier has chosen this random R, he can update the commitment to the witness and the slack error terms. So the commitment to the witness becomes the commitment to the witness of the running instance plus R times the witness commitment to the witness of the current R1CS. So the capital values represent the running instance and these I's represent the current R1CS. And similarly, the slack error terms get updated as the slack error term of the running instance plus R times the cross term. And there should also have been one term which is R squared times E2. But since our R1CS instance is just a normal R1CS instance, the slack error term for that is 0. So that's why we don't have the third term. And the scalar for the running instance gets updated as U1 plus R U2, but as U2 is just 1, this becomes U plus R. And then the similar thing happens for the statement X, which is X plus R times Xi, where again Xi is the statement of the R1CS and X is the statement for the running instance. So now after the prover has folded these two instances, he can prove that the folding was done correctly. So he can send proof by to the verifier, but it turns out that because we will be doing this folding, say suppose n times, the proof at each step is going to grow linearly with the round. So at each step, the proof is going to grow, and that's why we don't send this proof to the verifier. Instead, this f dash or this modded f dash now verifies the proof for some I instance. So as we discussed at the start of the presentation, the modded f dash function, it verifies that the folding was done correctly at the previous step, so that the prover doesn't have to send proofs for each iteration of folding. So to reduce this computation overload, the verifier circuit is embedded in this function itself, and this function now becomes this f dash function. So again, at each step, we are just verifying that the folding was done correctly, but we have not verified whether the function was computed correctly, right? So we have two steps. We have the function which is computed at each step, and also the folding which occurs at each step. So to verify the folding, we change this function f dash, which verifies the folding of previous step, but we kind of delay the verification of this function f. So the term used here is folding is similar to accumulating, so that we are accumulating, doing these checks on the function, and we only check that the function was done correctly at the end of the folding. So when we have folded all instances, at the last step, we verify that indeed the running instance was valid, which proves that these functions were computed correctly. So we kind of delay the verification of these functions. We only verify the folding at each step. So now let's see what happens at the last step. So when we are at the last step, the prover sends the round index or the round count, and the verifier checks that if n is the last count, then it will first verify the folding, and then it will verify the proof, which is sent by this prover, which verifies that, or which proves that the function has been computing correctly over these iterations. So the check for this function is only done at the last step. It's not done at each step. At each step, we just verify that the folding was done correctly. So now this is the diagram of the f dash, so that we have now the updated f dash or the modded f dash consists of this function f, which just computes the new output from the previous input. And within this function, we also have embedded this verifier circuit, where the circuit takes this running instance, which is capital UI, and then it also takes the current R1CS relation, which is UI, which is claiming that, which is a R1CS relation for the function at the previous step. And the verifier then outputs, verifies that the folding when UI and UI are folded, so this should be UI plus 1. So the verifier verifies that the capital UI plus 1 or the new running instance is valid. And this f dash also outputs this small UI plus 1, which is the current R1CS instance, which contains this running instance. And now we have a prover, which is just proving that the running R1CS instances are folded correctly into these current R1CS relation to give us the next iteration of the running instance. So one thing to note here is that the prover is outputting these witness to the running instance. So this is not a zero knowledge proof. So this is just a proof which does not hide the prover's input. So this is just an IVC proof that the folding was done correctly, because it is not hiding the witnesses from the verifier. But there is an issue here that this current R1CS, which is the small UI plus 1, it contains this running instance. And because the running instance is updated at each step, this running instance is going to grow linearly, and the small UI as will also grow linearly. So to avoid that, we just replace it with a hash function. So again, UI plus 1, which is the current R1CS relation, has these running instances. And this running instance it contains in itself the previous running instance and the public outputs, which is again the commitment to the witness, the commitment to the error term, the current round, the input to the previous round, and the output of the previous round, and the output of the current round. So as you can see that the running instance with each step is going to grow bigger with each iteration, because the previous running instance is also going to have these public outputs, and the next running instance will have the previous running instance and the public inputs. So the running instance is going to grow linearly in size, and to mitigate that, we just replace this UI with a hash function. So instead of outputting this running instance, we just output a hash. So now we have that the verifier at each step, it checks that this hash of the rounds, the current input and the initial input and the running instance is indeed equal to this public input and output of the current R1CS. So if I go here, so if you see in this diagram, we have that at each step it checks that the hash is equal to the R1CS relation, the public input and output R1CS relation, and it also outputs another hash instead of this R1CS. So instead of outputting the running instance, we output a hash function, which is this hi plus 1, and it in itself contains this running instance. And again, because the hash function is of constant length, the output will always be of constant size. So it will not grow with the number of iteration. And now the prover, will send. So one question you can ask here is, how does the verifier know this running the current R1CS instances, right? Because at each step, the verifier only is getting the hash function. So the verifier now gets this R1CS relation from the prover. So now the prover outputs the running instances, which is UI plus 1 and the corresponding witness. And it also outputs the current R1CS, which is UI plus 1 and witness I plus 1. So now the monet F dash will first, the verifier will first check that the hash was equal to this UI, the public input and output of the current R1CS, which is UI dot X, and the verifier gets this UI plus X from the prover. So the prover first folds the previous R1CS with the running R1CS, and then it outputs the running instance, and it also outputs the current R1CS, which is going to be used by the verifier of the next step to prove that the hash is indeed equal to this R1CS. And the verifier now will just verify that the folding was done correctly, and it will just output the hash I plus 1. So are there any questions up until now? And again, we note that this proof is not a zero knowledge proof because the proof in itself contains the witness. So the witness is not hidden from the verifier. So now we will look into what are the costs related to this verifier circuit, because we are embedding the verifier circuit inside our function f. So we define the recursion cost as the number of constraints for our new function f dash minus the number of constraints for the original function f, and we compare that which constraints are added to embed this verifier circuit. So the verifier now has to do, apart from evaluating the function, it also has to do these two MSMs, which is represented by this 2 times 2G, and these are done to update the commitments. So as we remember that the verifier was updating the commitments to the witness and the slack term by just multiplying the r's, which is a scalar, or random number, which is a scalar, which was generated by this hash function, times the R1CS witness. And it does the same thing to update the commitment of the slack term. And these two operations, because we are multiplying a scalar term with some vector, these are two scalar multiplications, and this is the additional cost related. And we also incur additional cost of the two hashes, which we do because uh, when we output these hashes, these are also included into the cost. And there's again one more hash, which is related to the fiat Shamir. So this is the hash which is used to generate this random challenge R. So in total, you have these three hash functions. And usually the fiat Shamir hash is done by incorporating a SHA hash and these two hashes, which is done in the verifier circuit. This is usually the Poseidon function, which is ZKstudy. So the verifier cost is dominated by these two MSMs, and it has these three hash functions, which are not that expensive. And the prover also has to do this extra step, which is it has to do the two multi-exponentiations, which are done when it is computing the commitment of the witness and computing the commitment of the slack error term. And these are two multi-exponentiations because we have to do this for Peterson commitments. We have to raise the generator to the power of the statement which we are committing to. So these are two exponentiations which are done by the prover, and it is costly to implement. So also, if you read, so there is a section in Taylor which describes that in addition to these two MSMs, we also have to do two exponentiations, which I did not understand. So yeah, I was hoping to talk to Google. So yeah, we can discuss this next time. And yeah, and also it turns out that when we commit to these cross terms, these are kind of expensive. So I was hearing this podcast where Ariel from Aztec, he was describing that it would be better in Nova if we would not commit to this cross terms, that it would decrease the cost. Yeah, so those are two things to consider about the cost of the Nova circuit. So now in the last section, we will see how Nova uses these cycle of curves to implement the verifier and the prover circuit. So let's briefly go over the concepts for the cycle of curves. So we have that if we define our elliptic curve, which is just coordinates xy over some group G, and this elliptic curve is defined by this group G, then it has a scalar field associated with the elliptic curve, which is denoted by this FQ, and it has an order which is P, which is a prime number, and then there is a base field associated with this elliptic curve, and this base field is F of P, where the coordinates of elliptic curve live in the field. So the coordinates of elliptic curve live inside this field Fp, and the scalar field if associated with this group is this Fq. So now if we have an elliptic curve, which is defined as EP, or it has a base field as FP, then the R1CS constraints system can be implemented in the field FP. So because these R1CS constraints typically require some group operations like point doubling, addition, this will require that the operations are done in this field FP. And this is the case because the coordinates of the elliptic curve are the elements of FP. So whenever we do these additions, multiplications, we have to use this field FP, or which is the base field. So group operations for the selective curve will be done in FP. But as we remember that in Nova circuit, we also have to compute these Peterson commitments, right? So these Peterson commitments are defined over f of q, which means that if the scalars for the commitments are defined over fq, and the commitment of the scalars is defined on this elliptic curve. So we have that our commitments to some statement are defined on this curve, but the statements itself live on this field, which is fq. So now if we try to go through the workflow, where we have at ith step, we have that the folding would require these group operations, because we are doing some R1CS operations. So this will require operations over this field FP. And because we are doing R1CS in this field FP, all our statements, or like the cross terms A, B, C, the instance and witness, they all are inside this, or they all are a part of this field P, or they are all are elements of this field P. But when we try to commit to these statements which are in field P, the commitments become now field. The commitments live over this elliptic curve, which is E of Q. So because once we commit, the field changes. So that's why there is kind of a mismatch of fields. So we have the R1CS relation, which lives over this field FP. But when we commit to these R1CS terms, the commitment itself now resides on an elliptic curve, which is EQ. And this EQ will have the base field, which is F of Q. So we have to change the base fields. So is this clear that why we need to change the base field for the elliptic curve? So again, the summary is that once we commit to the statements which live on some field F, field FP, the commitments will now be done on an elliptic curve, which is defined over some other base field. So that's why we choose, as we discussed in recursive snarks, we choose this cycle of curves where the base field of F, where for an elliptic curve, the scalar field is FQ and the base field is FP. And then we also define this another elliptic curve, which is EQ, which has the base field as FQ and the scalar field as FP. So the base and scalar field are interchanged in these two cycles of curve. And because the base and scalar field are interchanged, we can now do these computations, or we can now do these commitments, which are part of our folding circuit. So in the Nova paper, they only use one cycle of curve, and this is not very efficient when we try to write some code, or when we try to actually produce a proof. So in their code implementation, they use the cycle of curves, and these cycle of curves use again these two fields, which is FP and FQ. And now instead of one running instance, we'll have two running instances. So one running instances will be defined over this field FP, and the another R1C, another running instance will be defined over this field FQ. So to work to have more efficient computation, we employ the cycle of curves, and we have these two running instances, And each of these running instances have this modded f. And so first, if f is efficiently computational over fp, then we define our modded f dash, where the modded f dash is performing the computation of the function and is also folding. And this is done by this f dash function. So this is this bold f dash function, which has these bold lines, which are both doing the computation of the function and also folding the current computation with the running instance. But for the next running instance, we have this another modded function, which is f double dash. And this is represented by these two small lines, because this f double dash is not computing the function f. It is just verifying that the folding was done correctly. So we have these two different functions, where the f dash function is same as before. It is computing the function and it is also verifying the folding. When it is also doing the folding, where the second function, which is f double dash, is only doing the folding. It's not computing the function, because as we have said, that this function is efficient only on one field. So if the function is only computational efficiently computable over some field fp, then we have to have these two different functions, two different modded f dash or augmented functions. And now what will happen is that the modded f dash, the double modded f dash function, will verify the folding of the previous f dash function, and the next f dash function will verify the folding of the previous f double dash function. So these alternate, and these verify the folding of each other using this cycle of curves. Because because as we discussed, if we have an RONCS over P, the commitments will lie on this field Q. So to verify the folding, the verifier needs to have this field FQ. So that's why we have that these two interchange at each step, and they verify each other's folding of the previous step. So now this solution actually doubles the number of folding operation, because we have to cycle between these two curves, and that's why we have that instead of doing the folding operation n times, we're actually doing it n times. We'll be able to verify the folding of the previous step. So is this clear? Yeah, if you have any questions, please feel free to ask. So so there was this new recent paper which highlighted that this NOVA implementation, which was using this cycle of curves in their code base, had some security error, and they have updated their code base, and they have released a new paper where they are using this cycle of curves, but the setup is a bit different. So in their new paper, they claim that this F is efficient over both FP and FQ, and we now have, again, similar to previous case, we have these two running instances, and now both of the functions are doing the folding, and they're also computing the original function F. So both these functions are actually equal, and they are just doing the same thing, computing the function and verifying that the folding was done correctly. So they define a new function, which is this f1, which is a ring of function f1 and f2. And this f1 function represents the R1CS relation, which is the running R1CS. And this is done over fp, where the commitments of the statements in fp are in fq. And then we fold the R1CS for the next step folds the R1CS of the previous step. So we have these two R1CS relations where we have these two functions which are each doing computing the function f and also verifying that the folding was done correctly. So yeah, so this is how the NOVA uses the cycle of curves, where they have these two functions where both these functions are computing the function f and also verifying that the folding was done correctly, and each function verifies the folding of the previous function. So are there any questions about any of this, about the cycle of curves? So this was the last page, and yeah, we are done with the section 5 of NOVA. And yeah, and one last thing. So when we have these two running instances, each of these running instances will have will output of proof pi1 and pi2. So the verifier will verify these two proofs and then validate that the function was computed correctly, and also that the last folding was done correctly. So if there are no questions, yeah, let's meet. So I think we are going to study hypernova, and yeah, I'll discuss with you which sections should I present and which one he will present, and then we can go forward from there.
Next session we will learn hypernova.
Yeah. So we're done with NOVA. So that was NOVA. There is still some last section which actually explains how do you like make a ZKstudy, but it's not that relevant to read for future papers. So yeah, we can start with hypernova. And once we're done with hypernova, then we will read about the PCPs and the paper which he posted in the group.
Okay, sounds cool.
All right, guys, have a good weekend and see you next time.
See you.
Thanks,
Amit.
Bye-bye. Bye-bye.
Bye.